So very briefly, let me remind you that of what we have done so far. So far we arrived at a powerful duality between a 4-dimensional gauge theory and a 10-dimensional string theory. And this duality came from several different angles, so there were different perspectives hinting at such dualities. The decoupling argument by itself should in principle be a kind of a derivation or hint for the correspondence, but I think it does help to have all these other points of view that either reinforce or provide consistency for this picture, and altogether I think they provide very compelling evidence for this duality. But we should not take it at face value. We should of course check it and try to put it in very tough conditions, like when you test airplanes to make sure they fly, and we should see if it works or not. But here is all the evidence we could collect, and indeed it came from various different perspectives. And before we start, I'd like to comment a little bit more on this RG intuition that I mentioned only very, very briefly, related to this picture of the quark-antiquark and this paradox of how come the farther deadlines were delocalized, but we should have a string picture and so on. So I would like to comment a little bit more on this point 7 before we start with the main topics of today's lecture, which will be the geometry of ADS. Basically building on the tutorial that you solved already, I'll develop it in detail, and it's kind of a lengthy topic explaining all the issues of the geometry of ADS, and since we are starting a bit late, I will allow myself to go a little bit over time today. Okay, good. So before we move into the main topic, which is the geometry of ADS, I would like to make a few general comments about ADS-CFT and a few small comments about RG intuition. So about RG intuition, this is just this picture that, as we said, we can think of ADS as various copies of Minkowski space, where we have this coordinate z, and then we have various copies stacked up of Minkowski space. Okay? And one way of thinking of what's going on in ADS is saying that here, at the boundary, I have my quantum field theory. Okay? And then the idea is that here, so I have my quantum field theory in Minkowski space. So let's do the Euclidean version, R4. What we did so far was R3, 1 or R1, 3, but let's do it in Euclidean. And then here there are various copies of flat space which are rescaled. Okay? So here there is another copy of R4. And one intuition we can have, which we can try to associate, and again this is more or less just kind of a conceptual picture, we can think of this as the same quantum field theory at a lower energy scale. Namely, what we can say, which you see is rather intuitive, is that if you have your boundary, and if you are probing high energy, which means UV physics, so points close to the boundary, so this is what high energy would be, right, some UV physics, then their interaction will take place close to the boundary. So this region here would be some UV region. But if you were to consider more separated points, they would go inside and they would probe some low energy, some IR region. So regions that are further inside or further in the boundary, they are naturally, just by the nature of the geometry, probing high R versus UV physical processes. So more UV processes happen closer to the boundary, and infrared happen more separated from the boundary. Okay? So in particular, we have this picture, I remind you, of say our quark-antiquark. So there was a quark here and an antiquark here. Right? And now we say that and now I would like to say the following. Suppose that my space-time, it's not ADS. So in ADS we know what happens, it goes inside. But some other space-time, as some of you said, where the strings that go from quark to antiquark don't like to go inside a lot. They like to stay close to the boundary. Okay? So that with some space-time where it costs a lot of energy, it costs a lot of string length to go in, deep inside. This picture is the picture we would then perceive in the boundary theory, now forgetting about the holographic direction, just in the boundary, as saying that there is a flux tube between the two, which is thick, which is a thin flux tube. So as I am starting from the point, first I deviate a little bit, but then I stay at some fixed width, which is kind of the net effect of this flux tube. On the boundary, it doesn't spread out too much. Whereas when we have a space-time with the isometries of ADS, where if I put a quark and an anti-quark, the string goes in like this, so if I have this background, then it really is probing all scales, and this corresponds to a theory which has no scale, which is conformal, and where the typical Faraday lines are those of a conformal theory, where they are more spread out, and they are more something like this, like we are used to seeing in the lab, in a non-confining theory. Okay? So there is this intuition that we might want to, that some people try to make precise. Can we now make it more precise and start from a quantum field theory and introduce some other variable, which is the RG scale? At which scale am I considering my physical processes? And now I have 5 coordinates. I have the 4 coordinates of the field theory plus 1 coordinate of the energy scale. And I can try to see, will the physics combine nicely and give me something 5-dimensional, and will this new coordinate combine with the other 4 and give me some space-time? So people like Sung-Sik Lee at PI and others try to make this kind of picture more precise and see, can we really purely from the renormalization group derive some ADS CFT of sorts? And typically it's hard to make it sharp because of the nature of ADS CFT, because typically the examples are of this weak strong coupling type. That when something is easy and you can do renormalization and so on and you are happy, it typically does not correspond to classical limit because that requires some kind of strong coupling. But some general features you can find, and there's a lot of progress in this direction. And that's the last point that I wanted to add to this picture here. So now some broad comments about ADS CFT. So ADS CFT more broadly, this is just one example of ADS CFT dualities. This n equals 4 equal ADS 5 strings. There are many others. Some of them established rigorously and sharply, and some of them conjectured, and some of them where we only have one side of the duality and the other side is not even known. So let me make a few comments about the use of ADS CFT. One use is thinking of the ADS CFT as a definition of the gauge theory. Namely, I say, let me consider this theory in ADS, okay? So I consider this theory in ADS, and I use it to define my boundary theory. Right? In your tutorial, you saw an example. You said, let me consider massive particles moving in our homework. Right? So let's consider massive particles moving in ADS and see what correlation functions they define in the boundary. And they define some theory in the boundary. So that's a definition of a theory. People use this point of view often in other contexts, for example, saying that I put in ADS some relevant matter content that looks reasonable to describe a dual which would be a theory that would have some properties relevant for condensed matter. So this is more phenomenological. You don't know the dual theory, but you try in ADS to cook up some toy model, some phenomenological model, to describe something that would look a little bit like ADS. This is another example. You could come up with some space-time, where by hand you put now a different metric here. You say it's not ADS, but I'll put some metric where it costs a lot for the string to go in. So I put some different warp factor by hand. I just put and decide that the string doesn't want to go inside. And I know that this will lead to a quark-antiquark potential that will be confining, right? But I'm doing phenomenology, okay? I'm putting the result that I want. I put the space-time, I get confined, okay, big deal. Of course, what's interesting is that then you start computing other quantities. This one you put by hand, but now, in this theory, you now study, I don't know, scattering of mesons, or the spectrum of mesons, or so on, and then you see, does it start now to match experiment and to be a reasonable phenomenological approximation to QCD. So this approach of defining strongly coupled quantum field theories by using some theory in ADS was very popular a few years ago in condensed matter, also in the study of quark gluon plasma. Experiments were done at RIC, and there was some insight coming from ADS CFT. And I would say that nowadays there is a big activity in entanglement entropy, and in particular in entanglement entropy in strongly coupled theories, where I think it fits more or less with this first point of view, where we say that if a theory has a gravity dual, let's assume it does, and explore its consequences as a definition of the gauge theory. Okay, so as I said in the beginning of my lectures, Freddy will be discussing entanglement entropy a lot in the last week of the course. We can also turn it around and say, no, instead I will take the ADS-CFT as a definition of quantum gravity. After all, quantum gravity is the one I know how to define the least. Quantum gravity is harder to define. So I'll take some conformal field theory. It can be n equals 4 super Young-Mills, and then I know what the dual is, but it can be some other conformal field theory. And I will say, well, I will use it to define what I mean by quantum gravity. I'll say that quantum gravity is equal to this conformal field theory under this duality. And suddenly something that I had no idea how to define, now it's super sharply defined. Just a regular quantum field theory, conformal one, so it's the ones that are best defined and so on. Of course, what's crucial when you want to use this point of view is to have a good dictionary. Because you cannot just say, I'll define quantum gravity to be this conformal field theory, and then people ask you, okay, so how do we study two black holes merging? And you say, oh, I have no idea. But then it's not very useful. So it's useful to have some definition of quantum gravity, but the dictionary becomes very important. And then it's useful to learn about the usual dictionary in more well-studied examples, and learn how this dictionary goes. But it does provide very important insights into many paradoxes in physics, like black hole information paradox. Can there be a black hole information paradox? Can I send information in, be absorbed by the black hole, and disappear? Well, if whatever this process is describing has some description in terms of the conformal field theory, then the answer is no. Conformal field theory is a unitary theory. I put some state, I evolve it, it's just quantum mechanics. So of course not. Anyway, this is another point of view. And there is yet a third point of view once you do know both sides of the correspondence, which is as a guide, as a helper for solving gauge and string theories. It provides very important hints. As I emphasized several times, it's a weak-strong duality, which means that when one side is easy, the other one is hard. So if you trust this duality, or if you believe it for a few seconds, then it will often give you predictions. It will tell you, well, if this duality is true, then if you compute this quantity at strong coupling in Young-Mills, you will get this value. And then you say, okay, now I'll forget about the duality, and I will put up my sleeves, and I'll try to compute this quantity in strongly coupled Young-Mills. But I have no tools to study strongly coupled Young-Mills. Well, but now I have motivation to develop them, because at least I know what the result should be. So once you know, prove this in an exam, it's much simpler than derive some result, right? So once you know what you should get, it does help a lot. And indeed, our understanding, I think, of quantum field theory, it's fair to say, the amount of tools we have now increased dramatically precisely due to this ADS-CFT duality, or one of the things that really helped our understanding of quantum field theory and of string theory in general were these ADS-CFT dualities. Okay. Any question? Okay, so let's start the lecture then. Okay. Let me ask again, any question about the tutorial about the geodesics in ADS? Because the one about the geometry, it's going to be the topic of today's lecture. But about the geodesics, any question, conceptual question, or? Did everyone do the homework already? Or maybe not yet? Okay. Anyway, so ADS geometry. It's what we are going to discuss today. Learn a little bit more about the geometry of ADS. And I do hope that everyone did the tutorial, because I'm going to go relatively fast, precisely because you already did the tutorial, and I'm going to make further comments and develop further on the things that you saw in the tutorial. Okay? Okay, so let me start by reminding you that one way of thinking of ADS is as an hyperboloid, as you saw. So ds squared is equal to just the whatever metric I get if I take a unit vector where y squared is equal to minus y minus 1 square minus y0 square plus y1 square plus yd minus 1 square. So I take, this is my definition of an hyperboloid. So what I'm doing here is taking Y to be the set of unit vectors in R2, comma D minus 1. So if it is ADS 5, so this is the metric of ADS D. If it would be ADS 5, you see, I take R2, comma 4, so I take a 6-dimensional space-time, but I consider no unit vectors with this particular signature in R2, comma 4, right? Okay. So this metric here was the same as the metric we saw there, and there's some change of variables that I will discuss in the lecture, but which you also saw in the tutorial. So the way to draw this hyperboloid is one way is by saying that I have here y0, here I have y minus 1, and then this is the hyperboloid. So there is here a circle. And this rotation symmetry of y0 and y minus 1 is obvious here. You see, you can rotate y0 and y minus 1. Okay? And as I'm moving in this direction, which is the direction of the other y's, y1, and so on, the more I move there, the bigger the radius of this circle that I can rotate. So if these y's are 0, this is the circle of unit with unit radius. And as this increases, this factor here, I put it here and it gives me a bigger circle. So it's a circle that starts at 1 and increases in both directions. Okay? So this is what this ADS is. Note that there are here a few more comments. There are here 2 times. But and when I make this constraint and I look at this surface y squared equal minus 1, I get a space-time with signature minus 1 plus 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 plus, which has 1 time, so it's okay. And this is one way of seeing ADS. Now, this way of seeing ADS, it gives us something right away, which is a very powerful thing. So we see that there are, by definition of what Lorentz transformations are, they are transformations that preserve the norm of vectors, right? That's what rotations, or more generally Lorentz transformations, if I am not in Euclidean signatures, are. So if I do SO2, D minus 1, which are the Lorentz transformations that act on R2, D minus 1. So these Lorentz transformations right? These Lorentz transformations of R2, D minus 1, they preserve the hyperboloid. By definition of a Lorentz transformation, it's a transformation that preserves norm of vectors, so it preserves the condition y squared equal minus 1. Okay? So these guys immediately tell me that these are isometries of ADS. So I immediately learn that there are some Lorentz generators, let me write them explicitly, JAB, just the usual Lorentz transformations, that I can act, and they will rotate the x's amongst themselves, but they will leave the hyperboloid invariant. For example, if I do a rotation in the direction 0, minus 1, it just rotates this picture. It's an obvious symmetry of the way I drew it, this ADS2 here. Just these rotations here. Okay? And of course, one thing that should immediately call our attention, so then we make here a small comment, which is that SO2, D minus 1 is the conformal group in R1, comma D minus 2. So I encourage you in your head from time to time plug D equals 5 because we are studying ADS 5. So, and it also helps detect typos. So for example, if I put D equals 5, let's put D equals 5 in all the formulas so far. So we start with ADS 5. We get a unit vector in R2, comma 4, which is 6 dimensions. It's one more than 5. It makes sense because we put a constraint, so we go from 6 to 5 dimensions. Then we have SO2, comma 4. SO2, comma 4, yes. SO2, comma 4 is indeed a conformal group in R1, comma 3. Okay? So, sounds good. Okay, very good. So this is the statement that I made, that the isometries of ADS are in one correspondence with a conformal group. Here it becomes manifest. It is just obvious. The group, it is just Lorentz transformations in this particular variable. Now, if you come up with a parametrization, you come up with a particular parametrization, for example, one that goes to Poincare, and now you can ask, this transformation that was very simple here, it was just a rotation of the axis, how do I implement it in terms of some other coordinates? And it might be complicated. But whatever it is, it's what it is, and that's the isometry transformations in the other coordinates. And in this way, you could rather straightforwardly derive the isometry transformation that was in the exercise in terms of z and x in Poincare coordinates. Okay? That transformation is the one that one translated back to this embedding, so-called embedding coordinates, and they are embedded because they describe some coordinates that are embedded in some higher dimensional space-time, gives such simple transformation rule. But we will see it in more detail today. So this is one point of view on ADS. And then there was another point of view. To make contact with... I'm
sorry.
Yes.
X is the coordinate of...
Sorry. X is Y. Sorry, good. It's good because I do want to use X for something else. So, thank you. Thank you. Okay, then we have this, let's pick a parametrization. And there is this Poincare parametrization, one way of parametrizing and solving this constraint of the hyperboloid. Where we say that y minus 1 is 1 plus z squared plus x mu over 2z, y mu equal to x mu over z, and x d minus 1 equal 1, probably minus here, yeah, minus z squared plus x mu over 2z, where x mu is a point in R1, comma d minus 2. Okay? So you see that in the signature wise, I took mu to be one guy that has one time, and then the rest is space. I still catch the y0 of y. Okay, this is just to get this signature in Minkowski. Okay? All this can be done in various signatures, but okay, I'm trying to be consistent. Okay, so this here is a particular solution. It doesn't cover the full hyperboloid, in fact. It covers a patch of this hyperboloid. It covers part of it. For example, because, well, here it's maybe not very obvious, but if you add this plus this, add these two up. No, subtract them. If you subtract them, you see that you get z. This minus this is z. And z is positive. So it covers only the values when these two are positive. Okay? So under this parametrization, we saw that the metric ds squared, if I plug these values of y there, I get dz squared plus dx mu over z squared, which is the metric that we always draw, where we have this R1 comma d minus 2 in the boundary, and then some radial direction. Okay? Great. So just to practice a little bit with these isometries, note, for example, here in this picture, an obvious isometry is if I rescale z and also rescale mu. X, sorry. If I rescale x and z, this is obviously an isometry here, right? Do you agree? Let's see what happens in terms of y when I do this. When I do this, I get that, well, y mu doesn't transform, goes to y mu. But then y minus 1 goes to 1 over 2z times lambda minus 1, because 1 over 2z has weight minus 1, plus, and the rest has weight 1, lambda times z squared plus x mu over z. And what about yd minus 1? Yd minus 1 is similar, 1 over 2z times lambda minus 1 minus lambda z squared minus x mu over 2z. I'm just rescaling and seeing that part of it has weight 1, part of it has weight minus 1. Okay? So this is the transformation rule for these y's. Right? Now I want to point out that this is nothing but a Lorentz transformation of these y's, namely a boost of these y's. Let's see it explicitly. Let's do a boost. Okay, so we take a boost and we do the boost where y minus 1, yd minus 1. It's a boost of these two coordinates. It does nothing to the mu coordinates. Goes to, let me write a boost. A boost is what? Cos theta, sinh theta, cos theta. See, this matrix has unit determinant. Okay, and it preserves the norm, where this is a time, then that's a space, times y minus 1, yd minus 1. Okay? And if we act on these vectors here, you see that we get cos times this vector, sinh times this vector, right? And let's do it by head so that I write immediately the result. Let's write what the first component is. So you see y minus 1 gets multiplied by cos and yd minus 1 by sinh. So the first one by cos, the second by sinh. Okay? And now you see that there is part of it, the first one by cos, the second by sinh. Well, okay, it should work. Let's do it. Okay, I don't see it right away. I have to do it more slowly. So if I multiply the first by cos and the second by sinh, okay, let me try. I confess I'm a bit worried. It's not working in my head, but okay, let's try. It becomes cos theta times 1 plus z squared plus x squared over 2z plus sinh theta 1 minus z squared plus x squared over 2z. And here something else in the bottom. But this one here is equal to e to the theta, if I collect now powers of e to the theta, times 1 plus x squared over 2z plus e to the minus theta times 1 over 2z. Am I right? Yeah?
C over 2 should be the last one. Z squared on 2z.
Z over 2, yeah, that's right.
Pedro? There should be a minus sign in the yd minus 1 before the x mu.
Sorry?
Apparently for the x mu in the y d minus 1, there should be a minus sign. So it is 1 minus z squared minus x mu. At least that's what's in the tutorial.
Yeah, give me a second. I'm worried now. Okay, I should have checked these signs if I want to do it live. Okay, let's try. So let's check. Let's check that. I'm sorry. So I'll have to check. So if I do this square and minus this square, so what is this equal to? So when I subtract both, all the terms that are not cross terms cancel because they are the same. So only the cross terms survive. And the cross terms that survive from here, I get this term times this and this term times this. That doubles this term times this and this term times this. And the other ones cancel. So I get the squares just cancel, and then, sorry, let me do it a bit slower. So I get minus z squared. So I get 1 over z squared, and then I get minus z squared times 1 plus x squared, and from the top I get the same thing, so times 2. And indeed, this is not good, because this is not, if I add y mu square, I cancel. Ah, no, it's good, it's good. So there is a cross term, so there is a 2, there is a 4. So this is indeed minus 1 plus x squared over z squared minus. So when I add the y mu square, it cancels this term and gives me minus 1. So what is wrong? Sorry, let me think a bit. I did some simple mistake. Do you agree that it's okay? Did someone check the parameterization in the exercise? You should have found the minus sign, probably. You agree with me, right? This computation is correct, right? It gives this. What I want is the following. So what I want is to say that we get what we had above when we identify e to the theta to be lambda. So this is what I'm aiming at. But right now it's not coming out correctly. So, but it must. I mean, there's just some simple mistake somewhere.
Pedro?
Yes?
But that doesn't work. Your z squared cancels. You will just be left with minus 1 minus x squared. Right? Z squared cancels, and then there's
No.
x
This,
squared over
why? No. There is caution sinh, right?
No. That just that line. The minus the parameterization minus y minus 1 square plus yd minus 1 square. The last line of the top blackboard.
The last line of the top blackboard here?
Yeah.
I did a mistake?
It doesn't go from, the last step doesn't work.
The last step there doesn't work?
Because z squared cancels, you wouldn't get x squared over z squared term, you would only get an x squared.
But that's because...
That's because, as Martin said, so the parameterization should have 2 minus signs in yd minus 1.
Okay, that might help me. So a minus sign here?
Yep.
Let's try. I hope it works. So if I put a minus sign there, then instead the cross term that survives now is 1 here times z squared plus x squared, which now gives me what I wrote here, right?
Yep.
Okay, let's try and see what's happening now. So now there is an extra minus here, right? And with this extra minus here, now we get the cos theta, the e to the theta multiplies just 1 over 2z, and the e to the minus theta multiplies, the e to the minus theta multiplies 2z x squared plus z squared. Okay. Whew. Okay. Good. Thank you. Okay. Very good. So you see that that this boost is just implementing the dilatation. Okay. And as we wanted to see. So, and the second line you can check, it gives the right result. Oh wow, this was funny. Okay. But now, okay. So let's go on. So there are other boosts we could do, but we will do them in a particular case. Okay. But the conclusion here, let me just finish a conclusion, is that we see that the dilatation operator, which is the operator that does z, that dilates things, so it's z dz plus x mu d dx mu, right? This is the dilatation operator that implements dilatations, is nothing but the boost in the direction minus 1 comma d minus 1. Okay? So there is this boost that is giving that corresponds to dilatations here. Okay? So this is one of the generators of the conformal group, and the other boosts correspond to the other generators. Okay. Now, a few more comments. So, the boundary of ADS corresponds to the points where z equal to 0 in this Poincare coordinates. I remind you, this is when the metric is blowing up, so z equal to 0. And z equal to 0, if you see this Poincare parameterization, corresponds to large y's, right? Which is, of course, intuitive. If you see the hyperboloid, where is the boundary? The boundary of ADS is here. Where ADS is finished, eh? Right? So it's when the y's are becoming very large. Okay? So in particular, the boundary of ADS is the space of light rays in R2, d minus 1. Okay? So let's see. Let me just explain very briefly why. Well, there are many ways you can see it, but the first geometrically, so what's happening? So I have my hyperboloid. And there is here some light cone. And you see that for each light ray, it approaches, so each point here asymptotes to a given light ray. So giving a light ray or giving a point in the boundary is the same. So a light ray would be this. Right? So this would be a light ray, and this would be a point in the boundary, which is asymptoting to the same thing as the light ray. Okay? So the boundary of ADS is the same as the space of light rays. Each light ray gives you a point on the boundary of ADS. And another way of seeing is if you naively go to this parameterization up there, a more algebraic way, and imagine I just go to the boundary, so I plug z equal to 0 naively there, and then I rescale all my y's by z. If I just do it like that, then I get a parameterization of a null vector in R2, d minus 1. Okay? So you see that they are asymptoting to a null vector. So what is a light ray? Let's make it a bit more explicit. A light ray is some vector xa, which is projective, because if I have this point or this point, it's parameterized as the same light ray. So it's a point, and which is null. So x squared equal to 0. So this is a light ray. And when you want to specify a light ray, because light rays are parameterized by giving me null points here, they are all parameterized in the same light ray, it's often useful to pick a section to say, to single out a representative per light ray. Okay? So we can pick a section, some cut here, and different people cut in different ways, and you get different sections that correspond to different parameterizations. So one useful section, which is called the Poincare section, is just saying that my x is equal to the vector 1 plus small x squared over 2 x mu 1 minus small x squared over 2, which if you compare with what we had before, you see that it's nothing but sending z to 0 of the ADS Poincare parameterization. It's just dropping the z squares and then using this rescaling symmetry to get rid of the 1 over z. It is just what these vectors are approaching. Okay? But we forget now about ADS, and we can just think about these light rays here. Okay. So it's kind of interesting that the boundary is the space of, and it's also isomorphic to flat space, as we saw before, to R1, comma, D minus 2. So one way of thinking of flat space, if you want, is to think that flat space is the space of light rays in 2 more dimensions. So we could think of points here in space-time. Here is a point, here is another point. And someone could prefer to think here's a light ray in 2 more dimensions, here's another light ray in 2 more dimensions. Why not? From each light ray, there is a one-to-one map to a point here, you see, in R1, comma, D minus 2. So you give me a point, I complete it into a light vector. You give me a light vector, I rescale it until I find this representative. You see this representative is given by the product, by the property that these components add up to 1. So that's the section, a particular section where these guys add up to 1. So given some light ray, I rescale it until this happens, and I read off the space-time point. Given a space-time point, I plug it into this expression, and I get a light ray. So I can translate physics in flat space to physics of light rays in 2 more dimensions if I want, and recast physics in that language. It's kind of something that one could do. And one reason why this is a useful thing is that in this embedding language of 2 more dimensions, conformal transformations will be just Lorentz transformations acting on these light rays. So Lorentz transformation acting on these light rays, as we saw, corresponds to a conformal group. So something that naively is a little bit complicated to describe conformal transformations of points in flat space, in this higher dimensional point of view, it is just usual Lorentz transformations. Okay? So it's kind of a convenient thing. So for example, if I want to do, say, so let's see that more explicitly. So if we do boosts and rotations of my component capital X mu, which is the same as small x mu, well, this is the same as boosts and rotations of small x mu, of course. So this is the Lorentz group. But then there are more boosts we could do, which are not in these internal directions. We could do, for example, let's mimic what we did above, boosts of, in the direction x minus 1, x d minus 1. This is the exercise we did above, and you helped me fix the signs. So maybe you can help me again. Let's do it once more. Where under this, the vector x goes to what? Well, goes to, as we said above, cos theta, 1 plus x squared over 2 plus sinh theta, 1 minus x squared over 2. This one we don't touch, it's still x mu. And the last one becomes cos theta, 1 minus x squared over 2 plus sinh theta, 1 plus x squared over 2. Right? So I did a boost. Do you agree? But now you see that after doing this boost, I'm no longer in a Poincare section. Now these components no longer add up to 1. But that's fine. So now I say that this is equal to e to the theta, that's a rescaling, right? Times 1 plus e to the minus 2 theta x squared over 2, comma, e to the minus theta x mu, comma, 1 minus e to the minus 2 theta x squared over 2. Now here I am in a Poincare section. These guys add up to 1. Right? So what we do is we apply a Lorentz transformation. This turns the light ray into another light ray. I rescale to go to my representative. And now I read off, this is my new x mu. People call typically x prime mu after rotation. So what happened after rotation? My x got rescaled. And indeed, my x squared, which is what appears here, gets rescaled by the square and so on. Okay? So boosts in this direction, these correspond to dilatations. Okay? So let's just see the other ones, because the other ones are less trivial and they are slightly more interesting. To see the other ones, it's useful to go to light cone coordinates, where I parameterize my vector x as 1 x mu x squared. So you see what I did? This is just the sum, and this is just the difference, right? So we go to this light cone coordinates, where the section looks even simpler than there. And now we will apply boosts. So we will change our delta xa. So how does delta x change under some infinitesimal transformation? If I change it with some parameter, infinitesimal parameter omega AB, well, the change is proportional to omega AB. And then we have xa delta BA minus xb delta BA. Okay? The only way of putting the indices. So that's what we get from to do a Lorentz transformation. Okay, this is the general thing. So omega plus minus, we did. This was dilatations. And omega mu nu, we did. This was the Lorentz group. So there are only two more to do, which are what we're going to do now. Omega plus mu and omega minus mu. Okay, these are the new ones that we should do. Okay? Let's just do these ones next to see that it's very simple, and it gives something that in flat space would take a little bit more to derive. So this is a clear thing. So let's see what we will get. So let's first do, say, the transformation J plus mu when we contract this index mu with some direction B, just to get rid of the index. So what will this be? What will this give? Well, this will give a delta xa, which will be equal, let me do it in detail. So notice here, so I'll be very careful just so that you remember these ones. So I'm taking a lower index plus mu. So a lower index plus is an upper index minus. Okay? Plus delta A plus B dot X here BA. Okay? Where this vector B only has mu components. So we derive that there are two components that transform, delta capital X mu and delta capital X plus. Both of them transform. Delta capital X plus gives me just b dot x, and delta capital X mu gives me minus 1/2 x squared b mu, because x minus is just x squared. Okay? So we conclude that our vector x goes to, so now you see what happens to x. Delta x plus that was 1 is no longer 1. Right? Because I changed. But the definition of my section is that it's 1, so I factor it out. 1 plus b dot x. I factor this out, so now it's 1, so I'm in a good Poincare section. Now the second component changes. 1 minus 1/2 b mu x squared divided by this that I factored out, 1 plus b dot x. And the last component, I don't care, it is just the square of this one. And this, b is infinitesimal, so I should just expand this out. 1 minus b mu x squared, sorry, x mu minus 1/2 b mu x squared minus b dot x times x mu. Okay? So you see, this is a relatively complicated transformation. This is some x prime mu. This is nothing but a special conformal transformation. So you see, special conformal transformation are just particular boosts in the direction plus mu. Okay? Similarly, if we did j minus mu would correspond to translations. Okay? So we have the momentum p mu, we have the special conformal transformation k mu, and in total we have therefore dilatations, boosts and rotations, translations, and special conformal transformations, and this is the full conformal group. Okay, we just saw how to embed it in this SO2, d minus 1. Okay? Just to finish, to be precisely rigorous of why this is indeed a derivation without any loophole, let me point out that if you had used x equal to lambda, another section, which because it's another section, it differs by some lambda of x, times the x that you used before, Poincare, right? And if we compute the new induced metric, dx dot dx, okay, so something I should say is that dxp dot dxp, if you compute, this is just dx mu, so the induced metric is just flat space. But now let's compute it into some other section. And what happens when I compute in some other section? The claim is that you get lambda square of x times dx mu, which is conformal flat space. And the reason is obvious, because if your derivatives act on Poincare, it's obvious. I get just dx mu. Now, if the derivatives, both of them act on lambda, it's also obvious, because x squared is 0. It's a null vector. And if one derivative acts on lambda and one on x, it's also 0, because at dot dx is equal to 0, because this is just the derivative of 1/2 of x squared, which is 0. So either with one derivative acting here or two derivatives acting here, I get 0, and therefore my induced metric on some other section is just conformal flat space. Is just flat space up to some wild transformation. So these transformations here, that map that rotate and give you back the vector up eventually to some factor that I need to rescale to go back to my Poincare section, must be conformal transformations. Okay? Okay, this is the definition of a conformal transformation. So we see that actually more correctly, the more correct statement is that light rays, the boundary are light rays which are RD But that's also isomorphic to conformally flat space. It doesn't necessarily need to be R3 or R4 or R1, 3. It can be this space-time up to a general Wild transformation. Okay? That's also a good way of thinking about this boundary. And basically, it depends again on these different sections. We chose one section that corresponds to giving Minkowski, and there will be other sections that will give you other boundaries of ADS that would correspond, for example, to the cylinder that we discussed, which would be another possible way of thinking of ADS. And this is ADS in global coordinates that I'll describe in a second. Okay. This point of view also tells us what quantities do not change under conformal transformations. These are quantities that don't change under Lorentz transformations and rescalings of the axis. Right? If I build some quantity that doesn't transform under Lorentz and which is invariant under these rescalings, then I have some quantity that I know doesn't transform under conformal transformations. And you see that, for example, here is a quantity. You could construct xi, and you can dot it with xj. This is a Lorentz invariant. Right? But this is not invariant under dilatations, under rescaling of the axes. The axes are projective. They are light rays. So what I could do is divide by some other quantity, xk dot xl, and a convenient I realize this argument's a bit too fast. Okay. Yeah, okay. And put here well, not this actually, xk dot xl, xi dot xl, xj dot xk. So now if I rescale each of my vectors, right, notice that I can rescale each of them independently, I get something that's invariant. And it's all a Lorentz invariant because it's built out of scalar products. It's the only thing we can build which is scalar invariant. Notice that I cannot use x squared because x squared is null. So this is the only thing I can write which is invariant and which has no weight and which is Lorentz invariant. If you now use the Poincare section to see what does this correspond to, you easily see that each of these factors is proportional to the distance between the points, xj minus xl squared. So this becomes you just replace each factor by xi minus xj squared and so on. And this is what people define as a cross ratio or a conformal cross ratio. So starting with 4 points in space-time, you can construct quantities that are invariant under conformal transformations. And that's why in a conformal field theory, if you want to study correlation functions, they start becoming really interesting starting at 4 points, where you can start having non-trivial functions of these cross ratios that are not totally fixed by symmetry. Whereas if you do 2 and 3 point functions, as we saw in the lecture and as I think you probably saw already, 2 and 3 point functions are kinematically fixed and their dependence is fixed. For example, 2 point functions are just a power law. 3 point functions are also just a power law. But starting at 4, it cannot be just a power law because any function of cross ratios is perfectly invariant under conformal transformation, so I can never fix it purely based on symmetry. Okay, so this is how we can now see the isometries of ADS. You see, this is how you will see the transformations. You will just apply exactly the same logic, but to the full embedding coordinates and not just the boundary. Okay, now I'll go upstairs. Now, another useful parametrization of ADS, where we will see conformally flat spacetimes is really something that comes about, is so-called global coordinates. In global coordinates, I parameterize it as follows. So y minus 1, I would say, is cos rho cosine t. y0 would be cos rho sine t. And the other ones, yi, where I run from 1 to d minus 1, would be sinh rho times some unit vector. So it's a sphere. Okay? So you see, this parameterization is just what the picture almost tells us to do. So if I have an hyperboloid, where is the hyperboloid? Where is the hyperboloid? There's no hyperboloid. Sorry?
You just hide it.
I just hid it here?
Yeah.
It was here? Ah, here, okay. So you see that this y0 and y1, they have some radius, which I can call cos rho. And then cos rho, I rotate them, so I put some cosine t sine t that rotates here. Right? So t is here. Right? Time is here. And then, what's the radius? Well, it depends, it increases. The radius is related to how far away I am here. So there is some sinh rho, and you see sinh and cos are such that cos square minus sinh square is 1, so the constraint is satisfied. Okay, it's just a way of parameterizing how the radius of this circle here is increasing as I'm moving in this direction. And rho. Okay, so this is a convenient parameterization. And you see that in this parameterization, once I parameterize it, you see that normally in this picture, t goes between 0 and 2 pi. Right? Because it's enough to cover the hyperboloid. But that's not what we want. So let me explain a little bit. So in this parameterization, I now compute, and I get that ds square becomes minus cos square rho dt square plus d rho square plus sinh square rho and the metric of d minus 2 sphere. Okay? As I said before, it's always useful to see we are not doing a mistake, to put d equals 5 from time to time to see that the dimensions are working out. If I am in d equals 5, I say I am a 3 sphere plus 2 directions, so that gives 5 in total. It looks good. Okay? Just to see that I did not do a mistake. And you see what this space-time is. So as I take rho to infinity, as I study my boundary, this is just e to the 2 rho times minus dt square plus the derivative plus the metric of a d minus 2 sphere. So it is just a cylinder. There is time and there is a circle. So that's the boundary. Okay, so this is time, and this circle here is an S1 in this picture, but in general it would be an SD minus 2. Okay, and what is ADS? ADS fills in this cylinder. ADS fills in this cylinder. This would be rho equals 0, and this would be rho increasing from 0 to infinity. So ADS is like a solid cylinder, and the boundary of ADS is really the cylinder where I have time times a sphere. Okay? Just okay. So this picture is perfect. For example, if it's ADS3, it's exactly this picture. ADS2 would be a bit degenerate. This would be ADS2. There would be 2 boundaries, and in this case, it would be kind of okay. There would be just 2 boundaries. Okay, but ADS2 is like a small exception. I'll come back to it at the end, but that picture would be ADS3 and higher. Okay. What comments do I want to make? Okay, good. So this is one parameterization. Now, here the geometry of this space is very clear. It is just a box. So this is just a cylinder. Okay. If you study particles moving here. What particles do is that they bounce around and they move and they stay in this box. You throw particles, and if you have a particle quiet in the middle, it stays quiet. But if you throw it, it oscillates in this box. So it's a very nice box, yes. If you throw light rays, they get to the boundary and they come back. That depends on the boundary conditions you put at the boundary of the box, of course. You can put reflexive, absorptive, you can do whatever you want. So we have here a gravitational box. It's a special box because it's in fact a box that has no center. Because here I put a center, I drew it as being rho equal to 0, but I could boost it and shift rho to be any other rho. Any other boost that I do here would redefine slightly these variables, and there is no particular point. Rho equals 0 is not a special point in this hyperbola. So it's a nice box. It's smooth. It has no center. It has all this symmetry. It's probably the perfect box. Now notice that this t here belongs to R and not between 0 and 2 pi. So in fact, what global ADS is what's called the universal covering of the hyperbola. So the way you should think is that you have your hyperboloid and you wrap it many, many times. You put many, many paper wrapping it many, many times. And as you are moving around, you are not coming back to the same point, but to a different copy. You just put many, many copies on top of it. It's just an analytic continuation. You just say that things don't need to be identified. So as I go around, and then I go around one more, and then I go around one more, and I don't necessarily identify. So that's what's called a universal covering. Okay. And now, d tau, dt. What's dt? Well, dt is it's time translation, right? Which is conjugate to the energy in global time. So it's the symmetry generator. If I have stuff in this box with energy E, it is conjugate to this time evolution dE. Okay? And in our language of generators, it's a rotation between -1 and 0. So it's some rotation between -1 and the index mu equal to 0, which would be a linear combination of g plus mu and g minus mu, right? Because -1 is plus plus minus, which is what we saw before, was a combination of translations and special conformal transformations if I want to think from the point of view of the Poincare metric. Okay? So this would be what they would be in the Poincare picture. So let me draw it and explain what's going on here in these two pictures. Okay? But the point is that, okay, let me explain a little bit. So how do we see both pictures at the same time? So here I have my cylinder. Okay. And so this is the boundary of ADS. Let me add an index global to indicate in these global coordinates, which is R times a sphere. Okay? It's R times the sphere. Okay? Now, if I draw here, what is the Poincare, which region is covered by this Poincare coordinate, which, as I said, don't cover the full thing. Well, I said these global coordinates, they cover the full hyperbola. In fact, they cover it even more than once because of this universal covering. What about the Poincare coordinates? What do they cover? Well, they don't cover the full thing. They cover a napkin that you put on the boundary of this cylinder. So if you put a napkin like this, so you see this is a napkin that I wrap around and touch at this point here. Okay, so there is a surface here and here, and some interior here. This stuff here, this piece, is called the Poincaré patch. It's the patch of space that gets covered in global coordinates if I consider Poincaré. So here, it's very natural to consider time evolution. I can take a point and analytically continue it and move it in time. It is just dt, right? What does it correspond to in Minkowski space? Well, that's some more complicated generator, because you see that Poincaré is here. And in Poincaré, dt is a combination of P0 plus K0. I did something wrong here. Sorry, you should have corrected me. This is mu, but this mu is 0, right? So I wanted to emphasize that. So it's P0 plus K0. So it's a linear combination of what you would normally call zero, energy, right? And special conformal transformation. It's not a most naive operator that you would write down. But this is the combination, P0 plus K0. If you think from the point of view here of flat space, of being in this diamond, right? This boundary, this diamond is a copy of Minkowski space. So this diamond here is Minkowski space in d minus 1 dimension. So if you take Minkowski space there is a generator. If I study evolution under P0 plus K0, this corresponds to doing evolution in ADS, global time. Okay? So the spectrum of dt, which is this time evolution, is discrete because I'm considering energies of stuff in a box. So a box is a compact space. So the spectrum is discrete. And therefore, the spectrum of this operator, which is the same operator, should be discrete. Right? Which is a bit non-trivial, because if you think a bit, the spectrum of P would not be discrete naively, because it is just translations. I can put any plane waves I want. But this K is a special operator, right? K is a more complicated generator that grows as I'm going far away. It has this x squared dx, so it kind of confines by itself. And indeed, what we see based on this analysis is that this combination better has some discrete spectrum. And of course it does. And in fact, the spectrum of dt, which is just, as we saw, the generator G minus 1, 0, is actually a spectrum that we saw before, is nothing but the spectrum of the dilatation operator, which was the G minus 1, D minus 1. And the reason is basically, we will make it a little bit more rigorous now, but the basic intuition is that both are just two compact SO2s inside SO2, D minus 1, and therefore the spectrum of these SO2s should be roughly the same, and indeed they are the same. They are just related by analytic continuation, so they better be the same. It's not totally obvious right now, but let me make it totally obvious. But before, let me just present an important conclusion. So if this is true, I'll make it a little bit more manifest in 1 second, but I want to finish the implications of this statement. So then we concluded here that the energies of strings, now finally some prediction, of strings in ADS5, right? Well, this is equal to the energy of super Young-Mills in R times S3. Tell me, if you take Young-Mills and put it on R times S3, it's the same time. You see, the same T here and here. So if I compute energies of strings conjugate to ADS global time, is the same as energy of Young-Mills in R times S3. But because the spectrum of energies is the same as spectrum of dilatations, this is also equal to the set of anomalous dimensions of critical exponents of the dimensions that appear in the two-point functions of local operators in super young meals in flat space, say R4. Okay? So this is all kinematics. It all follows just from kinematics. And the only thing you might complain a little bit is that, okay, these generators were not exactly the same. But it was also not R4, it was R3, 1. So, for example, it's totally obvious, you would not raise any question, but if you do it in Euclidean to start with, here we did Lorentz inversion, right? So we had a time and space. And so this would be the Euclidean version. I will not erase it, but I will just leave it here. So what would change if we would do Euclidean? Let's point out here a few changes. So Euclidean version, light rays would not be in 2, d minus 1. The space-time now, the signature changes a little bit, becomes 1, d. Okay, just reshuffling a little bit the commas. Now, y squared equal minus 1, there's only a single minus sign. Okay, so we change a little bit this condition of the hyperboloid. When we do Poincare coordinates, now dx squared describes R4 and not R3, 1. yd minus 1 now contains a different minus sign. Of course, now I have no idea. Okay, we don't trust what I said before. I was wrong. So, okay, I don't know. But there should be some simple modifications. But the conclusion is that. And now if I do global ADS, actually global ADS now in the Euclidean version, where these components here, the first one are all plus, plus, plus. I don't need to use the last ones. I can use the middle ones to put the sphere. Remember that the sphere I put in the last ones? But now I can put them right away in the middle ones. And then it's totally obvious that now translations in this time, which becomes the Euclidean time, now I get really a Euclidean cylinder. So I draw exactly the same pictures, but it's really a cylinder. It's not a space-time cylinder. It's really a cylinder. Tau is just some space direction, like the circle is. So I get here a cylinder, and in these rotations, d tau, you see, rotations d tau are just rotations of the first and last coordinate, which were exactly dilatations in Poincare. Okay? So in Euclidean, the things are really go one-to-one, and I don't have to argue that they are two different embeddings, because changing embeddings, it is just putting a few i's to change who is time and space, and you might worry a little bit, but for example, what I'm pointing out here is that if you do it in the Euclidean version, things would work out perfectly, and you would conclude right away that energies are the same. The spectrum of energies in R times S3 is the same as the spectrum of dimensions in flat space. But back to this picture, there is yet another way, a third way of understanding what's going on, which is a beautiful way due to Mach and Luscher, which is to think, well, I have here something funny going on. So I have physics in flat space, and I'm studying correlation functions in flat space, right? But then what this picture tells us, forget about ADS-CFT, forget about ADS. So here I have flat space, and it looks like there is an analytic continuation of flat space to something bigger. It looks like I can now take points, and take these points, say here, I take 3 points here. But then I use this generator that allows me to translate points and analytically continue them up. And I can translate this point up, this point down, and start defining correlation functions starting from flat space, where I continue them. And now they live in a bigger space than flat space, which is this one here. Right? It looks like I should be able to do this. In fact, you can see that what you can do is you take this Poincare patch, and now put another patch up here. Put another copy of flat space here, and then another one here. So this would be the copy n equals 1. This is the copy n equals 2. The original Poincare space, the original Minkowski space would be n equals 0. And then you would put another copy down here. This would be n equal minus 1. Another copy here, n equal minus 2, and so on. Okay? So then you would go, and you start with Minkowski space. And now you have Minkowski, and then you have some copies of Minkowski, let's call it Mn, where n is 1 up to infinity, and below you have some copies of Minkowski, where n equal minus 1, minus 2, and so on. And indeed, you can start and think of this space as all these copies of Minkowski space, that they have some nice names. So these copies here, they are called the spheres of heaven. This is rigorous, it's the mathematicians that coined it like this. And this bottom part would be the circles of hell. Okay, so this is Mach and Luscher that explained why indeed in a CFT I can analytically continue physics that happens in a Poincare patch, in a copy of Minkowski into these infinitely many copies, which is just another way of thinking of this global coordinates r times SD. The fact that I can analytically continue, once more, is the existence of these generators that are symmetry generators, that are these particular fun combinations that allow me to move vertically and in this way leave the Poincare patch. Okay? So in this way, we see that there are, I don't want to erase this, this is important, so this is the main thing today, in R4. And here it's energy of strings. You see, this is an important entry of our dictionary, right? We are now saying that, look, if you compute dimensions or energies in Young-Mills, and I compute energies of strings, they better agree. Right? But the way to compute is totally different. Energy of strings uses some tools, energy of Young-Mills uses some other tools, so it's a very non-trivial thing if they will start agreeing. So this is an important prediction, but I want now to comment on the fact that there are these two ways of understanding these various equal signs, either in the way I just explained now, by choosing different sections and seeing that these are just different sections of SO2, or in this way of thinking about analytic continuation. Okay? So I'm almost done, so I will actually finish roughly on time. So in a in a CFT, we have, say, a 2-point function between two operators, for example. And I could consider circles here, okay, and consider dilatations, okay, dilatations that would dilate in this direction and map these circles one to each other. Okay. These dilations, if this would be just x dot ds, just dilatations. And if this distance here is y minus x, and if some operator has some eigenvalue under dilatations, we would get that e to the minus, well, we would get the usual power law behavior just because they get this distance with respect to dilatations. I should think of it as log of y minus x because of the way dilatations work. And therefore, exponential of log times the eigenvalue gives the usual power law behavior for correlation functions. Okay? So this is related to 1 over x minus y to the power delta. Okay, good. But now, think of a flat space. So think of that I start with flat space, Rd, and say that this is just dr squared plus r squared times a sphere. So say we are, say, a d minus 2 sphere. Okay. Does it work? Probably not. It's probably Rd minus 1. Rd minus 1, yeah. So suppose we start with Rd minus 1. I just have the d minus 1 such that when you put d equal 5 for AD as 5, it looks R4, and here as 3. Okay? And if I now do a wild, if I now say that R is equal to e to the t, so I go to the appropriate variables to describe this radial evolution, then this becomes e to the 2t times dt squared plus d omega squared. Okay? So what I did, now I can think of this, which is just a local rescaling of dt squared plus d squared omega. Yeah. Which by this factor here. So it's just a wild transformation of the cylinder. Okay, it's just a statement that flat space and the cylinder are related by a conformal transformation, which is the symmetry of a conformal theory. I can do local dilatations in a conformal theory. Okay? So in this way, you see right away that the same generator here now, right? The same, so now here I have a cylinder, and here I have t equal minus infinity, which would correspond to r equals 0, and here t equal plus infinity, which would correspond to r equal infinity. And then I have circles of constant time, which would correspond to r fixed. And time evolution in the CFT, in r times a sphere, is nothing but what was before dilatations in flat space. Do you agree? So this is another very straightforward way of establishing that in a conformal field theory, it's always true that energies of the conformal field theory in R times S times SD is equal to the dimensions of local operators in RD. Okay? It is just a simple consequence of this. So you see that there are two ways of going to the cylinder, which is kind of amusing. One way you can go to the cylinder is, imagine I start here with Minkowski space. Right? Now I take Minkowski, and I consider correlation functions. First, I do a weak rotation to go to Euclidean space, R4. And then in R4, I go to the cylinder by doing this radial quantization. Right? And this is one way of getting from flat space to the cylinder. Right? By thinking radially around the point, one point and another, and I get a cylinder. This is another way, it's different. Here I do have Minkowski. And I go to the cylinder not by going to Euclidean and then rotating and so on and doing radial quantization, but rather by extending and showing that Minkowski has an extension into these many copies of spheres of heaven and circles of hell that Mach and Lucia wrote down. But of course, consistency says that all ways should work and everything should be consistent, so it's better. So of course, it all works, but if you think that things don't seem to be exactly the same thing and that arguments seem different, I do think they are a little bit different. It's a little bit different. So one way of going from flat space to a cylinder is just radial evolution. And another way is by starting in Minkowski space and analytically continue them using these special conformal transformations and also getting in this way, but now to a Lorentzian cylinder, not an Euclidean one. Okay? This is just a small detail. Okay, I think I would like to make a few comments about the symmetries of ADS2, but I will leave them for tomorrow when I will summarize these main conclusions of the geometry. And again, this was more or less just a review of some of the aspects of the tutorial with some more details. But if you have any other questions about the geometry of ADS. So the summary is that ADS is a very interesting spacetime, and we should make use of its various different incarnations. On the one hand, it's a very symmetric space. It's just an hyperboloid. It's roughly a sphere up to some signs, right? So it's a very symmetric space. You just rotate this hyperboloid. You have these Lorentz transformations that leave it invariant. It's a very, very symmetric space, right? It's, if you say, I want something which is as symmetric as a sphere but contains times, that's ADS. On the other hand, it's a box. Box is a very useful thing. So it's a gravitational box. In physics, we like boxes to put things inside and do experiments. And if you want a box where you can put gravity inside in a consistent way and have some good box where you have boundaries but they are not put by hand in a way that breaks all your symmetries and so on, this is ADS. ADS is a nice box with a nice boundary, and we can do experiments at the boundary, send stuff from the boundary, see what happens inside, receive stuff. So it's awesome for doing experiments in gravity. And if the box is large enough, if the box is very large, you see, it means that there you can expand close to rho equal to 0. So you go to ADS and you expand close to rho equal to 0. And what do you get if you expand close to rho equal to 0 in this box? You get flat space. Which is, of course, the intuition. If I have a huge box, I don't see the box. It looks like flat space. So if we take a very, very, very big box, which means you can focus on the region around rho equals 0, we are just doing flat space physics. But we are doing it in a controlled way, where we have this box to regulate our theories and to make sense of them. So this is, as you can imagine, why I like this box picture very much. And there's also yet this other way of thinking about this Poincaré picture. And the Poincaré picture is a very useful one as well. I don't want to say it's worse than the other two, because it's the one that naturally comes when we derived it, right? When we derived it, we did not land on the box or on the hyperboloid. We landed on this copy of Minkowski and then different foliations. This was because there were this picture of brains, and things came from the brains, and this was the brains generated the space-time, so this foliation picture was more natural, and it came around naturally there. And it should not be a surprise if I tell you that when we want to come up with the dictionary, typically the dictionary comes about more easily in that picture, because we go back to the derivation and ask, how would picture particles scatter in the previous derivation? And we go and complicate a little bit more the derivation and see, oh, then probably this is the dictionary. Then once you have it, it's trivial to translate it to any other of these pictures by analytic continuation and so on. Which this analytic continuation gives you a new duality if you want. We have n equals 4 super Young-Mills in flat space being dual to ADS5 times S5 strings in, say, Poincaré coordinates. And now a new duality is n equals 4 super Young-Mills, not in flat space, but in R times S3, is equal to ADS5 times S5 strings in global ADS. Okay? It's a minor thing, it's just a small analytic continuation, but it already gave you a new duality. And this new one did not come naturally from a brain construction, but it comes from all these kinematic considerations that we made today. Okay? So here is an entry of the dictionary of ADS-CFT, one entry that we would add. So here is an example. If I want to define quantum gravity like this, here is an example. If I say, what is the energy of the black hole? I put some black hole and test some energy, and at least I want to study these black hole mergers and study some state which has some total energy. Well, now we know. It should correspond to some state in Young-Mills that has some big energy. So what could you do? Take your Young-Mills state and act with a super complicated composite operator on the vacuum. Like take, you see you have these scalars, take trace of phi to some gargantuan number, act with this operator on the vacuum, it generates a very highly excited state. It's literally like hitting with a big hammer your experiment. Now this will generate a linear combination of many states, but with a big overlap with very heavy operators. These heavy operators will in particular contain black holes. So this is already some kind of hint on how we start establishing these correspondences. If we could make it precise, then we could ask lots of fun questions about the physics of black holes. That, as I said, because we can make the box large, should be the same as the physics of black holes in flat space. So from this point of view, we have in ADS-CFT a window towards learning about quantum gravity. And in fact, up to now, it's probably the most rigorous and the best established window by far that we have. Okay, enough of geometry. Thank you. Questions? Yes?
Just have one question. Previously, when you talked about the RG picture just in the beginning,
yes.
And when you write down the metric that is like split into the dx's and the dz's.
Yeah.
How do you? Where does the RG coupling come in that metric so that you can see?
For example, that metric is invariant under rescalings, right? Because I rescale x's and z, and it's an isometry of the metric. So that is the proper metric to describe a theory which has no RG. They have a theory which is the same at all scales. Right? Let's think of RG in the following way. Let's say RG is what tells me how correlation function changes when I change the distance of my points. Right? If I go to long distance or short distances. This metric tells you that nothing special changes. If you take, say, 3 points at 3 axes, or 3 points at twice the distance, well, nothing changes if they just go twice as deep in z. When I guess it just dilate the full picture. Right? You compute some process, just make a dilatation of it. Right? You draw your picture, now draw a bigger picture, and that's it. So physics are not changing as I go between different scales, so there's no scale in the problem. So that's what you expect for a conformal theory. On the other hand, if your space-time is such that your metric is such that you don't want to go inside a lot, then there will be a huge difference in your, say, correlation functions. If you consider nearby points, then they just fly. Or if you get separated points, where they are now forced to stay and propagate for a long time. Now there is a new scale, which is this height of z. where it starts to cost lots of energy to go in. And now this would describe typically correlation functions compatible with an RG for a massive field theory and not a massless one, where there would be indeed some different scales. And for very short distances, I'm very close to the boundary, which is ADS, and I don't see it's a massive theory. That just means that my energies are so big that I don't see any masses of particles I have. But as I separate and I go to low energies, I start seeing that the theory is not conformal, and instead things decay with exponential behavior and like a massive theory. Now, typically those examples where the theory is not conformal, we have very little examples of theories where we control well the metric we should put. Then people do more phenomenology. They put some metric which cuts things off, and they do. It becomes less controlled of an approximation, but still a useful tool to get some intuition. Was it too slow? Because it was the same as the tutorial, so I'm afraid that maybe it was a bit too slow. But okay. I thought it could still be useful to summarize a little bit. Okay, see you tomorrow.